So welcome to the online lecture for the subject of power electronics, and the topic of our today's session is two transistor model of thyristor and triggering circuits. So let's see the two transistor model of SCR. So before the coming to this concept, so we have to be familiar about the thyristor operation. I mean the SCR operation there. So and of course the turn on methods also. So coming to the two transistor model. Okay, so before that, look at this symbol of this SCR. So it is a 4-layer, 3 junction. Here it is a junction J1, J2, and J3 here. So and the layers are PN, PN, and the terminals are anode denoted as A, and the gate denoted as G, which is connected to the P layer, and the cathode K. Okay, so this setup, I mean this 4 layers are bisected into 2. So look at here, the middle 2 layers, that is N and P, are bisected into 2. Okay, so it appears as a PNP, and this is considered as one transistor. Let it be T1 or Q1, so that's up to you. Okay, next is NPN. Okay, consider this as another transistor denoted as T2 or Q2. So in some of the books it is represented as T1 T2 or Q1 Q2. Okay, so here are the terminals: anode, gate, and cathode. So why we have to bisect this as two, or why we have to consider it as a two transistor model in the sense? So we can analyze this performance. I mean, how we are going to perform this turn on and turn off. Okay, so its behavior also similar to the transistor, that is this SCR also performs like a two transistors. Okay, so that's the case. Okay, so basic operating principle of SCR is understood by the two transistor model of SCR. It is a combination of P and N layers. So as mentioned here, here basically it is a 4-layer and it is bisected into 2. So consider as PNP, and another is NPN transistor. So figure represents the equivalent circuit of the SCR. So we'll see further. So this circuit. Okay, so look at here. So it is an PNP layer. Okay, so with the terminals anode, gate, and cathode here. So this collector current is connected to the another transistor. Okay, and these two transistors are interconnected through the collector terminals. Okay, so look at here. If we design the equivalent circuit, so then how it appears means, look at the right side figure. It is anode terminal. So this is the considered as a transistor denoted as Q1 or T1, and this collector is connected to the base of the transistor Q2 or T2. Okay, the collector current or the collector terminal of first transistor Q1 is connected to the base terminal of another transistor. Okay, and the collector terminal of second transistor or Q2 or T2 is connected to the base of the first transistor. Okay, so that is the case. So these two collector currents are connected to the bases, to their bases. Okay, so that is the equivalent circuit here, and the gains are here alpha 1 and beta 1 for the first transistor, and the gains are, I mean collector base gains are for transistor T2 or Q2 is alpha 2 and beta 2. So both alpha and beta are the collector base gains. Okay, so and the respective terminals, that is collector, emitter, and base. Here emitter terminal for the first transistor is anode. Okay, so that is IA, and the emitter terminal for the another transistor Q2 is IK. Okay, so anode, cathode, and gate. Sorry, anode, cathode, and gate. So emitter terminals are here for first transistor is anode, and the emitter terminal for the another transistor is K, cathode. Okay. So I hope mm, it is fine up to now. So that is this is about the equivalent circuit of the two transistor model of the SCR. So what are their what about their configurations and all? Okay, so let's see what how this is how the equations are represented and all. Okay, so from the figure you can see the base of the transistor T1 is work as the uh, collector of the transistor T2, and the collector of the transistor T1 work as the base of the transistor T2 or Q2. Okay, so as per the transistor leakage current equation, so this equation is already it is defined in transistor basic transistor equation there. So from this equation we are going to start now. So it is obtained from the I mean it is collected from the basic transistor equation, and it is this is similar to this and the same basic transistor there. The collector current IC. Okay, so this is a normal equation there. IC equal to alpha into IE plus IC B naught, or okay, IC B naught. Okay, so this is the IC is the collector current and IE is the emitter current, and collector base leakage current is treated as IC B naught, okay, or ICBO. Okay, so this is the normal transistor leakage current equation. Okay, so this is already predefined there in the transistor part. Okay, so where alpha is the uh, current base gain. Okay, and ICB naught, as mentioned, ICB naught is the leakage current of the common base transistor. Okay, now this equation is similar to the both the transistors, that is Q1 and Q2, or T1 and T2. Okay, so uh, it is equated with the same, I mean this equation is used for these two transistors also. Then how the equation appears means, for transistor T1 or for transistor Q1, the emitter current is equal to the anode current and collector current IC1. So IC1 equal to alpha 1 C. So IC1 equal to gain alpha 1 into collector current, sorry, emitter current, that is IA. So IA plus leakage current. In the first transistor, the leakage current ICB01 or ICBO1. Okay. So where alpha 1 is the, and I mean this one, the suffix 1 represents uh, the parameters refer to the first transistors. Okay, and 2 represents the for the parameters representing for the second transistor, I mean IC, IB, and alpha, beta likewise. Okay, so that's the case. So similarly for the second transistor, what may be the collector current equation? IC2 equal to alpha 2 into collector emitter current. So what is the emitter current here? This is IK. Okay, so alpha 2 into IK plus leakage current. The secondary transistor, sorry, the second transistor leakage current ICB not 2. So this is about the collector current equations in the transistor 1 and 2. So which is bisected, I mean which is treated as the combination of two transistors. That means this SCR is treated as a two transistors. Okay, so this bifurcation also, this equivalent circuit is also just treated as across the junction J2. Okay, so between the junction J2 only we are going J2 only we are creating this two transistor. Okay, right. Next, where alpha 2 is the current gain, I mean it is also already mentioned here. Alpha 2 is the current gain of the transistor T2, and the emitter current of the transistor T2 equal to cathode current IK. So this is the emitter current for the second transistor, and for the first transistor emitter current is IA. Okay, so since both the collector currents, that is sorry, yes, both the base and collector of the transistors are interconnected here. That means for the first transistor, the collector current, I mean the collector terminal is connected to the base, and for the second transistor, the collector terminal is connected to the base of the first transistor. Okay, right. So thereby the anode current gives the combination of, so IA gives the combination of both the currents, so that is IC1 plus IC2. So substituting the values of IC1 and IC2, so what is IC1? Alpha 1 into IA plus ICB not 1, and IC2 equal to alpha 2 IK plus ICB not 2. So substituting these values in IA equal to IC1 plus IC2, so we get this equation, that is IA equal to alpha 1 into IA plus ICB naught 1 plus alpha 2 into IK plus ICB naught 2. So by substituting the value of IK, what is IK here? This is the emitter current. So before that, you can just think about here. So this is the anode terminal, gate and cathode. So this current has to start from anode and it has to reach to cathode. So if we consider as a transistor here, so the ground part is IK here, that is the emitter part. So this is a combination of IG plus IA, because for triggering we are applying the gate current. So I hope you know the reason why we have to prefer the gate triggering method. So that is discussed in the turn on methods of SCR. Okay, right. So when we apply the minimum gate current, so that is one of the input for the transistor, and the another input current is the anode current. So this two combinations, that is IA plus IG, gives IK. Okay, so IA plus IG, so here it is mentioned. Okay, so IK equal to IA plus IG. So substituting this, we get IA equal to alpha 1 into IA plus ICB naught plus alpha 2 into this IK value is substituted here. Okay, IA plus IG. Okay, and equating this equation, that is IA, because why we are highlighting this IA means that is the input current, or that is the load current. Okay, so since the SCR, we are going to perform the controllable operation, means we are going to control the switch, so that the current is controlled in the switch. Okay, so how this current is depending upon the which parameters, I mean what are the controllable parameters and all, we can trace out from this equation, that is the anode current equation. This is IA equal to alpha 2 into IG plus ICB naught 1 plus ICB naught 2 by 1 minus alpha 1 plus alpha 2. Okay, so this is the equation, and this combination alpha 1 plus alpha 2, so this is the gain of the current base there for the two transistors, that is for alpha 1 for the first transistor and alpha 2 for the second transistor. So this alpha 1 plus alpha 2 is depends upon the, I mean this emitter current, that is IE. Okay, so if there is increase in the emitter current, sorry, if there is increase in the gain values, obviously there will be increase in the emitter current. So this is how we are going to control the gain value, so that the IA is controlled here. Okay, that is the anode current, so which is the load current in the two transistor model, not only the two transistor model but of course the SCR also. Okay, so this is how by adjusting the gain value we can control the current in the switch. Okay, so if we consider it as a transistor, how this SCR is performed is analyzed. So that's all about the two transistor model of SCR, and we'll look into some more points about this two transistor model. Okay, so working of the SCR can be easily explained by two transistor model, and that's how that's what now we discuss. So for a simplified analysis, you can refer the circuit also in the right side bottom. So this is the circuit. Two transistors are connected here. So their collector and base are interconnected here. So for this, through the gate terminal, the input is connected through a switch, and the load is connected here, that is a load resistance is connected, and an external source is there. Okay, so as per the figure, you can see the supply voltage V and the load resistance R is RL is applied here, and here we have to first assume that the voltage V is less than the breakover voltage, as is the usual case, because the input voltage may not be exactly same as the breakover voltage. So I hope you know the importance of breakover voltage. So that is the maximum voltage uh, required for the SCR. So that gives the maximum rating of the operating voltage of the SCR. If we exceed the breakover voltage, or if it reaches the breakover voltage, there may be chance of avalanche breakdown and the SCR may conduct. So this process is nothing but the forward voltage triggering. Okay, so as discussed earlier, and when the gate is opened, so look at this. So gate open in the sense, already here we are using an external source. When the switch is opened here, the gate current will be 0. Okay, so gate in the sense, this collector and base are connected, so IB equal to 0. Okay, so therefore the IB is 0. So for the base of the T2, see, so the collector of T1 is connected. So no current flows through the collector of T2 and hence that of T1. Since there is no input here, so this transistor will be in turn off. Okay, next, the same case when the switch is closed here, when the switch is closed, so what happens, a small amount of gate current flows through the base of T2, obviously the collector of T1. So since the current is flowing through these two transistors, if even though if one of the transistor is fed with an more gate current, obviously the second transistor also comes to the conduction, so that there exists the flow of current. Okay, so that is the case. I will just read out what are the points mentioned. So whenever the switch S is closed, so here we have closed the switch, a small gate current will flow through the base of the T2. So this is the base. Okay, so which means the it collector current will increase. Okay, so the collector current will increase, therefore T2 and T2 also, T1 also will conduct. Okay, this action is accumulative since an increase of current in one transistor cause an increase of current in another transistor. So since we are it is connected to the T2, okay, obviously the T1 also will conduct. As a result of this action, both transistors are driven to saturation. That means both transistor comes to the conduction, and a heavy current in the sense that depends upon the load there, okay, flows through the RL. So that is R suffix L actually. This is RL load. Okay. So under such conditions, this SCR is considered as switch is closed. So overall, this setup I am saying. Okay. So this setup is appeared in the, see here. Okay, so this setup is completely closed. That means the current is flowing from anode to cathode through the with the injection of gate current to a certain extent. Okay, after that, once the switch is completely closed, this gate current is no longer existing. Okay, so there is no need of this gate current. Even though if you remove the gate current, the switch will be continuously in on position. That means the current will be continuous flowing in the switch. Okay, so that's all about two transistor model of SCR. So hope you have understood this. Thank you. Okay. Uh, Next we'll start the SCR triggering circuits. So in that R and RC triggering will be discussed. So R triggering circuit. So before that, we must. I would like to once again so highlight that these are the current commercially not used methods, but not to analyze how by using a resistor. So how can we make this ACR to turn on can be discussed now, but commercially it is not used in any in outside of the market there. That is R triggering and RC triggering. Most preferred method is the gate triggering method. Okay, so in that let's discuss this resistance triggering circuit. Okay, so this is the look at the circuit in the left hand side. So an input voltage Vs equal to Vm sin omega t. So where Vm is the maximum voltage and omega is the angular frequency in radians per second. So a DC load or any load, if you consider it as a resistive load, it will be quite flexible. So consider any load, and the load voltage is V naught there, and the input voltage is Vs. Okay, and the where R1 is the stabilizing resistance. Okay, so or it is going to limit, or it is going to stabilize the current there, where R2 is the control resistance, okay, which is used to control the current in the gate there, gate circuit there, and a diode is connected in series to these two resistors. So in order to avoid the negative voltage across the gate terminal, okay, so where R is the limits the voltage at the gate terminal. So this is then SCR. So in the terminals, I hope you know, that is anode, here it is cathode and gate, okay. So in some of the textbooks it is mentioned as this resistance is acts as an sink also, so for the gate terminal, okay. So that is the case. So this is the setup of, I mean, this is the configuration of the, so a resistance triggering circuit, and the drop across the thyristor is mentioned as vt, v suffix t, okay. So load voltage is v naught, and input voltage is Vs, which is our phase supply, or of course, uh, we can analyze differently in case of the DC there, and the voltage drop across the thyristor is mentioned as Vt, okay, and the gate voltage is mentioned as Vg, okay. So what is the importance of this gate voltage means? So that is the voltage required so that it draws the current, okay. This gate and cathode, between the gate and cathode, so a small amount of voltages appeared, and this gate, through this gate we are allowing the minimum current, okay. So through this gate terminal, okay. So let's get into the operation of the circuit, okay. So let's see the circuit operation here. So when the input supply is given, okay, so initially there will not be any current drawn because the switch is completely open. See, okay. So yes, the switch is opened here, and this resistance will be very high, okay. So very high in the sense, what is the relation means, look at here. So this R1 is greater than or equal to Vm by Ig max, okay. So the maximum gate current, because we need we have to consider the extremities, that is the minimum gate current and the maximum gate current, okay. So when the maximum gate current is reached, so further no need of any gate current because the switch will be completely turned on, okay. So that is the case. So a minimum amount of current will be flown through this gate terminal, okay. So when we are going to adjust this resistor R2, okay, so when we are going to adjust this resistor, variable resistor R2, so this gate current is going to be uh, changed, okay. I mean, it is going to vary. So because of the uh, increase in the gate current, okay, so what happens, this switch will be coming to the turn on stage, because this method is also nothing but the gate triggering, okay. So there we are allowing the small gate current. So before that, what about the position, or what about the condition of this SCR means, it is in forward blocking state, okay. So forward blocking state means anode is positive and cathode is negative, and there is no gate current. So soon after applying the gate current, what happens, slowly the switch comes to the forward conduction mode, okay. So the same thing happens here also, okay. So but by using the resistor R2, we are adjusting the gate current with the help of the input supply. So soon after, when the gate current reaches maximum, that is Ig max, so what happens, the switch will close, okay. So soon after, when the switch is completely closed, what happens, so all this resistance will be biased, so completely for the positive half cycle. So this switch will conduct, okay. So a DC voltage is appeared across the load, okay. So all these things I will explain in further in the waveforms clearly. So before that, I may explain you the circuit operation, okay. See, so soon after, when the switch is closed, what happens, this current, the load current will flows through input to load to across thyristor to source. So this is the current flow direction, okay. All this resistance will be biased here, okay, when the switch is completely closed. So that's about the circuit operation of the R triggering circuit. Okay, so once again I will highlight the points what are they mentioned. That is R1 is the gate current limiting the resistance, or it is considered as the stabilizing resistance, and R2 is used to vary the gate current and hence the firing angle. So firing angle means actually that is the parameter used to control the uh, gate current. Okay, so when the firing angle is minimum, okay, so firing in the sense, so taking some action here actually. So we are making the SCR to turn on, from turn off stage to turn on stage. Okay, so when the current is minimum, okay, so when Ig is minimum, so the switch will be in forward blocking state. So when it reaches the maximum gate current, the switch will conduct. Okay, so that relies on this, I mean this gate current is depending on, I mean the controllable resistance R2. Okay, so based on the adjustment of the resistance, this current is controlled. If the current is controlled, obviously the switch is controlled. That means if we are going to control the gate, obviously the switch current, that is the anode current also, is controllable. Okay, so and see the relation Ig max equal to Vm by R1, and R1 is greater than or equal to Vm by Ij max. So this is the relation. So based on this, we have to select the potentiometer. Okay, so in earlier days they are using the potentiometer there. So the choosing of potentiometer is based on this relation. Okay, so R limits the voltage at the gate terminal. So this is the uh, gate terminal resistance, and the selection of the R is depending on R less than or equal to Vg max R1 by Vm minus Vg max. Okay, so as mentioned, this diode is used to avoid the reversal of current. That means there may be chance of reverse current flows. So that this diode will prevent. Okay, so diode prevents the buildup of negative voltage at gate terminal. Okay, so so it's a simple circuit, or it is also a half wave circuit, because it conducts only for the positive half cycle. For the negative half cycle, what happens? Anode is fed with negative and cathode is fed with positive. It comes to the reverse biased condition. Okay, so in the reverse biased condition, or that is in a reversal operation, the switch will not conduct. It will not conduct for the negative half cycle. Okay, so that is the case. Okay, so what are the disadvantages of this? Means the performance depends on the temperature and SCR characteristics. Okay, and the minimum phase angle is typically 2 to 4 degrees only. So that is the reason why it is not commercially preferred. So the control over, that means uh, the on and off capability, okay, is very less. That means the control is achieved very less. So this is the firing angle alpha. So this is the delay. Okay, so up to this it will be in off state, and this is the total turn on stage. Okay, so this drop is appeared across the thyristor. Okay, so and the maximum angle control is 90 degrees. Okay, so we'll see clearly in these characteristics. Okay, let's see the characteristics, I mean the waveforms for resistance triggering of an SCR in half wave circuit with a DC load. Not only particularly a DC load, obviously the output will be DC. So either any of the circuit elements are preferred there. Okay. So look at the figure A here. So this is no triggering of SCR. So no triggering in the sense, see this is the input voltage here. So the first figure is the in figure A. The first figure is the input waveform. So all the x-axis represents the omega t in radians per second, and the y-axis represents their magnitudes. That is the input voltage, gate voltage Vg, output voltage V0, load current or the output current I0, and the voltage drop across thyristor Vt. Okay. Let's see. When there is no triggering means the gate peak voltage. So VGP is the gate peak voltage, and VGT is the uh, so, so gate peak voltage, and the VGT is the threshold voltage of the gate, or you can consider as the maximum gate voltage. Okay. So when it is below the threshold voltage, okay. So as you know, there should be a minimum current in the thyristor. I hope you remember this holding current and latching current. So when the current falls below the holding current, so the SCR will goes to turn off. So when the switch has turned on, so the minimum current has to be started is the latching current. Okay, so that's the difference here. So obviously, even though if we start raising the gate current, okay, so the layer junction J2 will not disappear. So slowly the depletion layer gets reduced. So after that, what happens? The anode to cathode, the current flows. Okay, but because of the junction J2, it will be in blocking state. So there will not be any current through the switch. Okay, so obviously there is no voltage also. So that is the reason why here that is V naught and I naught. There is no waveform. So completely the input what is fed to the circuit is appeared across the thyristor. So total voltage drop. So whatever the input is there, so that is blocked across the thyristor. So that condition is the forward blocking state. Okay. So that is the reason input is as is at the thyristor across the thyristor. So there is no output voltage and there is no output current because the gate current is not sufficient. Then what we are going to do? So then we are going to adjust the resistance. Okay. So then we are going to adjust this resistance R2. So that means if we are adjusting resistance R2 means what happens? This gate current is variable. Okay. Since the resistance initially will be high, so we are going to reduce this resistance so that the current is controllable here. So the current is adjusted, the gate current is adjusted until the maximum current when it reaches the maximum current. Okay. So suppose, so if I have made equal to the this gate peak voltage is equal to VGT. When the voltage is sufficient, what happens? The switch will conduct, the SCR will conduct, and because of this delay, so as I mentioned, so we are going to apply the gate current. So thereby some saturation is required for this SCR. That means some transition time will be there. So this is the delay here. So this is the off state, and in this stage is the on state. This I'll 1 second. I'll change the color. Yes. So this is the on state. That means this peak is the on. Okay. So and because of the if the load is resistive, the current waveform follows the voltage waveform. Okay. So with some reduced magnitude. So the magnitude is very less. Okay. So what about the negative half cycle? The negative for the negative half cycle, the switch will not conduct because if you look at here the circuit. Uh, for the negative half cycle, what happens? The anode is negative and the cathode is positive. So it comes to the reverse bias condition. So the switch will not conduct. Okay. So what happens? Completely whatever the input is fed, it is appeared across the switch. Okay. So that is the reason why the waveform is appeared across the thyristor. So at the voltage at the output side, that is the V naught, the voltage is 0 here. Okay. So what about the current? Since there is no voltage, obviously there is no current also. Okay. So only for the positive half cycle it is conducting. So this alpha is depending on your adjusting resistance. That means that depends upon the gate voltage here. So you look at this. Okay. So similarly, What about this with increase in alpha? Okay, if I increase, uh, sorry, if alpha is equal to 90 degrees, so that is the maximum uh, conduction there, because look at here, this is for a half cycle, and this is the maximum voltage. So I hope you can see the dotted lines at 90 degrees conduction. So this is the maximum conduction. So if alpha less than 90 degrees, this is not greater than 90, it is less than 90, because the maximum conduction control is for resistance firing is 90 degrees only, 0 less than, alpha less than or equal to 90 degrees only. Okay, so let us consider as 45 degrees. So how can you consider as 45? See, half of the cycle means, I mean, in a half cycle, the 50% of the waveform is at 90 degrees. So in that 90, in that 50% means 45. So let us consider as 45 degrees. Okay. Now I have adjusted the resistance up to a 45 degrees. That is VGP is greater than VGT. So what happens? Uh, Voltage is appeared. So this is the total output voltage, and this is the delay. Okay, this voltage drop is appeared across the thyristor. So whatever the waveform is missing here, so you can see this a small portion of the waveform is missing, that is appeared across the thyristor, and the current waveform follows the voltage waveform with a small magnitude, with a reduced magnitude. Okay, and again for the negative half cycle it will not conduct, so the negative half cycle is completely across the thyristor. So finally, so we have to focus on this output voltage, output current, voltage across thyristor, and what about the for the input, that is the gate current. So this is how, by adjusting the alpha, that is by adjusting the resistance, okay, the gate current is adjusted. So with the gate current adjustment, obviously the voltage is controlled. Okay, so with the control with control voltage, obviously the current is also controlled here. Okay, so this is how we are going to control the current in the thyristor, that is the SCR, so that the load current is adjusted, because the load current is drawn through the switch only. Okay, so through the switch the current flows. Here we are going to adjust in the uh, current of the switch, that means the load current is adjusted. So how hence our objective is, uh, I mean, we have reached our objective. Okay, so and next we'll get into the RC triggering circuit, as similar to the resistance triggering circuit. So this is also same as the resistance triggering here, but in addition to that, a small changes are made. So let's see. So this is the circuit configuration of the resistance capacitance triggering circuit. So RC is nothing but the resistance capacitance triggering. Okay. So so same, the input voltage Vs equal to Vm sin omega t, and a load is connected. Okay, so and the same, the controllable resistance is R. So diodes D1 and D2 are connected. Okay, and a capacitor C to a this SCR. So what are our objective? I mean, what we are going to perform here, in the sense we have to make the SCR from off state to on state, and how the control is achieved. So all these things we have to so justify. Okay, so in this circuit, so capacitor charges during the negative half cycle through D2. See, when it reaches to the negative half cycle, for the positive half cycle means anyhow this is same. That means I'll mention you the direction. See, the current flows through input to load to resistance to through diode to gate, as well as when the switch is partially conducting. So what happens? This current also, this load current also flows through the SCR. Okay, so because of this high resistance, what happens? A minimum amount of current flows through the gate. Okay, so what about D2 means when there is an 80 half cycle. Okay, so sorry, before that, this capacitor is going to be charged here with a positive and negative polarity. Okay, I repeat once again. So during the normal operation, that means during the positive half cycle, so the current flows through load to resistor to diode to gate terminal. So this will be very minimum value, that is Ig minimum. Okay, because initially the resistance will be high. Okay, so a small amount of current only flows through this diode. Okay, so next, at this moment, the capacitor is going to be charged with polarities positive and negative as mentioned. Okay, so during the negative half cycle, okay, so that means here here it is neutral and here it is phase. Okay, so I hope you can see this away from also. This is for positive half cycle, that is here here it is phase and here it is neutral. Now for the negative half cycle, here it is neutral and here it is phase. So what happens here? Okay, so through the capacitor, so that means the current flows through here the capacitor and through D2 to source. Okay, also because the resistance is very high, so uh, the small amount of current flows through resistor also, but we have to notice that earlier the polarities are positive and negative. Now the capacitor has to discharge and it has to charge. I repeat once again. Now, initially, capacitor is charged with polarities positive and negative. Now, the polarities are reversed in the negative half cycle. Now, here it is negative and positive. Okay, so before stored energy is released through the diode D2. Okay, so that is the case. So uh, that's what here it is mentioned. When the SCR is turned on, capacitor C is suddenly discharged through D2. Okay, so D1 protects the SCR during the negative half cycle. Okay, so this negative energy will not be fed to the this uh, gate terminal because the diode will not conduct for the reverse will not conduct to the reverse bias condition. Okay, so and the advantage over R triggering circuit is this controls up to 180 degrees. So earlier it was up to 90 degrees. So that is 0 less than alpha less than or equal to 90 degrees. Here 0 less than or equal to 90 less than or equal alpha less than or equal to 180 degrees. Okay. So the maximum control is achieved up to 180 degrees. And the resistance RC is chosen based on this relation here. That is RC greater than or equal to 1.3 T by 2. Okay, so and the relations you can note down. Vs is greater than, that is the input voltage is greater than or equal to R into Ig minimum plus Vg minimum plus Vd1. So in order to generate the minimum gate current and obviously the minimum gate voltage and the minimum diode voltage, so these are all the uh, saturating voltages or the threshold voltages. Okay, so based on this we have to select the input. Obviously it will be around it will be greater than all these values only, no need to particularly highlight this. So from this, if you want to highlight the resistance value, what must be the controllable resistance means it should be less than or equal to Vs minus Vg minimum minus Vd1 by Ig minimum. Okay, so this will be order of very few amps only, few milliamps only. It's not a big issue. So that's the anyhow that's the relation. Okay, and what about coming to the waveform here? So look at this input waveform. This is Vs. Obviously the x-axis is omega t radians per second here. So this is the input voltage Vs, the output voltage V naught, and the voltage drop across the thyristor Vt. Okay, so this is the waveforms for the RC half wave circuit because it conducts only for the half cycle. So for the next half cycle it will not conduct, as we have seen in the resistance triggering. Okay, so figure A, this figure represents for the high value of R. Okay, high value of R means the drop is very high, that means the firing angle is more. Okay, so this firing angle is more, so the output voltage will be less. So maximum drop is appeared across the thyristor. So this is the maximum voltage drop. Only a small portion is appeared. So this is the minimum voltage. If the alpha is high, the output voltage is minimum. If alpha is less, if the delay is less, we look at here. So the maximum voltage is appeared. So this is the maximum voltage appeared. So the drop will be less. So this is the drop. And for the negative half cycle, so look at for both the waveforms, the negative half cycle is completely appeared across thyristor. So this is the drop. So there is no voltage across the load. I mean, there is no output voltage. Okay. So in for the negative half cycle, it will not conduct. It will be zero. Okay. So that's all about RC triggering circuit. So hope you have understood this two transistor model of thyristor and the resistance and resistance capacitance triggering, that is gate firing circuits of SCR. So hope you have understood the session. So thank you.